Welcome back, chemistry fans. Today, we are going to finish up gas laws. We've got a bunch of seemingly unrelated topics, mostly centered around something called diffusion. So let's jump into it right away, get us through this last topic. Okay, so diffusion is a term that you have heard before. It is whenever things become less dense, whenever things start to spread out. Well, in chemistry, what that means is that we are going to try and figure out how it affects its density, what some of the properties are when that occurs. So one of the things we need to remind ourselves is the density formula, that it is mass over volume. So we're going to utilize that and we're going to calculate some details. Now, one of the things, though, that we could use to our advantage is that we can use the mole map if we are at STP. So don't forget, we have some tools that could calculate that volume for us, or we could calculate the mass if we have the ideal gas law, PV equals nRT, or we could use this 22.4 as our volume if we are at STP. If we're not, then we're going to have to rely on some other tactics. Okay, so let's jump into this right away and let's find out what we need for this. So you're reading this problem. There's a sample of gas and it originally has a mass. Okay, so if we are going to be looking for the density, find the density, we've already got the mass. So half of the story is already accomplished. But here's the problem. It originally occupies 392, and you're saying, well, by golly, let's get the density. Let's roll it in there. But these were the original set of conditions. So we are going to have to set up ourselves a combined gas law problem where we are going to have one set of original conditions and we're going to have to settle for, or we're going to have to solve for the new set of conditions. Because we were originally at 392, 32 degrees, and a new pressure, and then it changes to STP. Now, let's figure this out as to what it is. So we got our original pressure of 0.95. We have a volume of 392, and we have a temperature. We have to add to that 273. So 32 plus 273 is going to be clear. Let's try that again. 32 plus 273 is going to be 305. Now, what we're going to do next, though, is we're going to set this up at the new set of STP conditions. We don't know what the volume is. That's what we're going to need to plug into our formula. But we do have STP. Standard pressure would be 1 atmosphere, and the standard temperature would be 273. So then we'll have the volume, if we solve for this, that we can plug into our density formula. So I've got 0.95 times 392 times 273 as we cross multiply, divided by 305. And what we get is our new volume is 333.3. We could just round that to 333. So I've got a mass of 26 and I have a volume of 333.3. We will figure out what this density is, 333.3, and we would get 0.078 grams per liter. Now, generally, density is in grams per milliliter or something like that. So since they didn't tell us, we're just going to leave it at grams per liter, and that will be our density. Okay, moving on. So we have now a new scenario, though. What if, we've never dealt with this yet, what if our gas is not pure? We are going to need to be able to still measure some of the properties. Well, fortunately, gases mix together well, and it is about the amounts. It's not about any other details. So the pressures will correspond to the amounts. So if we were to use the ideal gas laws to solve for the pressure of one gas, we could do the same for the other gases, combine them together, and they add, they're summative. So the pressure of one gas plus the pressure of second gas will be summative. You can add them together, and it will not need to be based on what the material is. It's just how much the material is. So this is the focus of Dalton's law of partial pressures. You can add together partial amounts to get the total amount. So let's see what happens with this practice problem. So it says the total is equal to 0.99. So that's the sum. And so we have these two gases. We have A and B. Well, portion of one of them is 0.05 and the other one is 0.02, but we don't know what the third one is. So we're trying to figure out what is that third part. Well, this just becomes a math problem. 0.99 subtracted by 0.05 subtracted by 0.02, that will tell us what this third gas is. So let's just do that. 0.99 minus 0.05 minus 0.02, and we get 0.92. So this gas, whatever it is, air pressure is 0.92 atmospheres. Very simple concept. Moving on. There is a word in gas laws that pops up frequently. It's vapor. Now, this is the English spelling of it, so it'd just be VAPOR for us. But a vapor needs to be distinguished from a gas. Now, they are treated the same way as far as gas laws are concerned, but a gas is a different state of matter. It has been fully converted over to the new state of matter at the current temperature. But in a vapor, you have two states of matter existing in the same container. You have liquids and you have gases. Well, these materials are then mixing with air. So the vapor is actually not pure at this point. It is mixing with whatever gas is in the container or whatever is in the air. So the liquid is transitioning, it's evaporating, turning into, or vaporizing, turning into the next state of matter, but there's still both of them there. And when we measure our vapor pressure, it's usually always needing to be sealed. So we need to have a lid on our container. And the true definition of vapor pressure is how much force is being exerted back on the surface. So this gas that is evaporating, it needs to be then measured as to how much it's pushing back on the surface, or how much putting on the lid, or how much is putting on the walls, whatever that is. So it's how much pressure that new vapor is pressing against some surface. One of the details that you need to understand about vapor pressure, however, is that it is the same no matter how big the container. So air pressure is the same on a small container as it is on a big container. Even though it's spread out over a larger surface area, it still has the same force on all surfaces. I would like for you to be able to distinguish between evaporation and boiling. Evaporation is whenever you have the liquids turning into a gas, but the pressure of the vapor is less than the atmospheric pressure. How you know that you are greater than the atmospheric pressure is if it starts to boil. Boiling is slightly different, and that's whenever these vapor pressures, they have more energy than do the air particles, and so the gas starts forming inside of the liquid. It's very eager to get out and escape and become a gas out normal. All right, the last little details that we need to figure out are then how do we deal with this ratio if we have a mixture of gases. This is again going back to the Dalton's law of partial pressures, and it's got your old friend in here, the mole ratio. So sometimes it won't be as easy as just adding together the gases. Sometimes what we're going to have is a mole ratio. Now you got to remember what mole ratio is. It's moles of the solute divided by total moles. Now, this was a difficult process for some of you on question number 11 in the last test. You have to be able to remember how to calculate moles from the mole map many times. So you may be given grams, you may have to convert them into moles and then plug them into this formula for mole ratio. Well, then, if we know what the mole ratio is, we apply that same ratio to the partial pressure ratio. So in other words, if I have 50% of gas A and 50% of gas B, it's going to make up 50% of the pressure, each of the gases. If the pressures were 30 and 70, the pressures would only be 30% related to A and 70% related to B. So we're going to use those. And another way that we could think of those equations, if we have several different gases, not just two, well, we still need to add them all together to get the total moles. So we would take the individual gas divided by all the total gases, multiply it by the total pressure out here. These are all total pressures. And that will give us the partial pressures of those individual gases. Okay, so let's get up to the last slides here. We've got just two more topics, one more topic, but this is our next to last problem, penultimate. So in this scenario, we're wanting to figure out the partial pressure of each of the two gases. There are, I'm sorry, of the two gases, yeah, so there's an N2 and an O2. We've got their mole amounts. So let's add those together. I think you could probably do these in your head. The total number of moles is equal to 0.032 if you add those together. So the mole ratio for A and the mole ratio for B are two different values. So I would take the individual amount. Oh, let's not call them A and B. Let's call them N2 and O2. So the mole ratio for N2 would be 0.03 divided by that total moles. The mole ratio for the oxygen would be 0.002 divided by 0.032. So let's put those into our calculator. 0.03 divided by 0.032, and we get 0.9375. So in other words, 93%. And if we do the exact opposite, you're going to find that it's the 7% roughly. And it's 0.0625. All right, so we have our two mole ratios. We have our total pressure here is 0.52. So we would multiply by that total pressure, and these will then give us our two partial pressures. So this is 0.032, and that's in atmospheres. And then 0.9375 times 0.52 is 0.4875 atmospheres. So those are our two partial pressures. So it's just another way of solving for a partial pressure if they only give you mole values and they don't give you what the pressures are, like we had in the first example. All right, diffusion and effusion. They both sound the same. You are familiar with the term diffusion. It means to spread throughout containers, spreading out as far as possible. Effusion means that the gas is escaping through a tiny hole. They are both governed by the exact same formula. This formula is called Graham's law. Graham's law says that the inverse of the masses of two gases, the inverse of the square root of two gases, is equal to the ratio of the velocity, or it could be the amount of time that it takes for the gases to pass a certain point. So time and velocity could be equally related here. So this little v, this is velocity, let's spell that correct. That is velocity, which is the same word for speed. And these are the molar masses. These are not the weights of the compounds. These are the total weights of the compounds. So it wouldn't be like you're given 50 grams of N2. It's what the weight of the molar mass is off the periodic table. All right, so let's jump into these last little formulas. Oh, here it is again. Rates could be also utilized instead of time or instead of velocity. That could be the same. Let's now jump into it. So in this problem, we don't know what the two gases are. So we're going to set up a ratio. But I do know that one of the gases is hydrogen. So now it does not matter which you choose to be on top or bottom. You want to choose this to be gas A, or you want to choose this to be gas B. It does not matter. So I'm going to choose this to be A, just to make it simple. Now, in the formula, it is the molar mass of B over the molar mass of A equals the rate of A over the rate of B. So it says that this hydrogen effuses 0.5 times faster. So it's 0.5 times faster than the other material. So for every 0.5, the other one is going 1. Now the molar mass of hydrogen is 2 if I go on the periodic table, but I don't know what the molar mass of this other gas is. I'm sorry, it's half as fast. I'm sorry, it's not 1.5, it's not 0.5 times faster, it's 0.5 times as fast. So it's saying it's slower is what that means. So mathematically, algebraically, we need to get rid of this radical. So what we're going to do is we're going to square both sides. So 0.5 squared gives me 0.25. And whenever I did that, that got rid of the radical. Now this is just cross multiplication. 0.25 times 2 means that x is going to be equal to 0.5, which is very, very odd, because that would say that the molar mass of this thing is 0.5. I'm not sure that that's quite correct. I'm going to fix that whenever I get to class. But for the purposes of this video, that would be our answer on that one. Okay. Moving on. Last topic, we already know about the kinetic theory of gases. So I'm going to add one little detail on this. We know that the faster you get, the more energy you have, the hotter the temperature, the further apart, the more likely you are a gas. Here's the last little detail I want to add to it. The smaller you are, the faster you are. So in this final example, I want you to tell me which of these two gases is going to effuse, or translated, which one of these two is going to move faster. So let's go and get their weights. Chlorine weighs 35.453, and there are 2 of them. So that is a total of 71 grams. And methane weighs 16 if I add up its weight. Which one of these is going to move faster? It's going to be the lighter one. The lighter one moves faster. It will effuse faster. All right, this is everything that we need to know and understand about the gas laws. Thank you for staying with me. I know this was a hodgepodge of topics. Hopefully you can piece it all together and start to understand it once we practice it a little bit more for homework. Talk to you soon. Bye-bye.